In this video, we're going to talk about vectors. So let's get right to it. Okay, so what is a vector? So vector is a new type of quantity that's going to be very useful for us. So vector is a quantity that has two characteristics: the magnitude. Magnitude is kind of how big this thing is, and a direction. So it points in a particular direction. Opposed to that, kind of in contrast to that, like a regular type of quantity that we use, like numbers that we use, we'll call those scalars. So scalar is a quantity that only has a magnitude. So the way to kind of think about these, one way to distinguish them is to think about the difference between what velocity is and the speed, right? So I should be using color. So for example, let's say you're driving up I-5, I-5 North at 60 miles per hour. So if you're driving in your car going 60 miles per hour, 60 miles per hour is the magnitude. So that's the speed, right? And what velocity is going 60 miles per hour north towards the I-5 North direction. So if you include the information about which direction you're traveling, then that becomes the velocity, right? So if you forget the direction, you just remember how fast you're going, then you have a scalar. Okay. One way to represent the kind of visual geometric representation of a vector is using an arrow. So if we draw an arrow that looks kind of like this, we're thinking of the length of the arrow as the magnitude, and the direction is from the tail to the head of the arrow, right? So it's going in that direction. Okay. When you're thinking about a vector, kind of geometrically speaking, you don't have to think of a vector as something that's kind of stationary or put or glued to a certain point. You can kind of put it anywhere you want and it's considered the same vector. So what I mean by that is, let's say I have like a two-dimensional vector right here. Let me actually draw a better vector. Okay, if I draw a vector here and kind of copy, I can place it there, I can place it here, I can place it there, I can place it at the origin if I wanted, I can place it over here. All of these are considered to be the exact same vector. So it doesn't matter where it's located in the coordinate system. The only thing that matters is that it has the same direction and it has the same length. Okay, so if you're talking about an arrow, you could kind of describe it in many different ways. So one way to describe it is just kind of say what the magnitude is and call that R, and measure what that angle is. So usually the typical thing to do is you draw direction that's going the same direction as the positive x-axis, and you measure the angle in a counterclockwise direction from there. So if you note the length and the direction from the positive x-axis going counterclockwise, then that gives you a vector. So if you want to write it down and not just draw it, that's how you can represent it. Another way to represent a vector could be describing the components. So you can kind of imagine kind of draw like a right triangle here. How many units does it go in the positive x direction? And how many units does it go parallel to the positive y-axis? And then record that information. So go talking about kind of break it up into components going in the x direction and the y direction, and writing it that way. So that also captures the same information. A lot of times, I think the components form is a little bit easier to work with, because if you wanted to add something, it's much more convenient to have it in that form. But you are expected to be able to go back and forth from these two ways of describing a vector. Okay, so you have to use a little bit of trig to kind of go back and forth. If I kind of draw an angle there, and then maybe if the hypotenuse has the length r, you can kind of write down the x component by, well, cosine of theta is the ratio between adjacent over the hypotenuse r. So x over r is equal to cosine theta, or if you multiply r to both sides, that's what you get. You could do the same thing with sine. Right? So if you have the magnitude and the angle, you could write down what the component x and y is. And if you have the x and y component, you could write down the r and the angle. So magnitude you could write down using Pythagoras theorem. Okay. And angle, you'll have to use some trig, right? So let's see, the tangent of the angle is opposite over hypotenuse, sorry, opposite over adjacent. So arctan of y divided by x. So that's one way to kind of go back and forth. Okay. All right. So we could talk about vectors in 2 dimensions, 3 dimensions. To distinguish it from talking about a point in space that has a particular address of x, y, and z component, remember that vector could be placed anywhere. So to distinguish it from 0.23 or 2, -3, and a vector that has components 2 and -3, you could kind of write it this way, right? So usually when we write vectors, we're going to draw kind of an arrow going on top of the variable that we're using. So that's how we write it. And the components are separated by comma, and it's kind of put together with this left and the right angle brackets. And if you have a 2-dimensional vector, it just has 2 components, x and y. If it's a 3D vector, you'll have 3 components, x, y, and also direction going towards the z component. Okay. There are other notations where people use. So unfortunately, some books might not distinguish the 2 different notation, the points and the vector, and you have to determine it from context which one they mean. Thankfully, we don't have to do that in our book. So our book uses this angle bracket notation. So that's what I'll use. Other notation that's common is use a kind of boldface font to write those variables. So that's kind of hard to do on this application. So boldface, or sometimes people underline it, or sometimes people put a squiggly line beneath it. But I think this arrow notation is the most common. So that's what we'll use. Okay. All right. So sometimes it's good to kind of connect the vector and a point as well. So when you do something like that, we call it a position vector. So actually, this is a 2-dimension. So let me write it this way. So if we go 3 units to the right in x direction and 1 unit in negative y direction, this is the point P. So that's a particular point that you're not allowed to move around. It's just a point on space. But you could kind of associate this point with a vector that points from the origin. And usually people reserve the letter O for the origin. So a vector that points from the origin to point P will be that vector 3, negative 1, right? So if you place a position vector at the origin, it points to that point with the address that has the same components as the vector and a point. I hope that makes sense. Okay, but if we're talking about a vector, we're allowed to move this around. So, when you're talking about it as a position vector, it's convenient to place it at the origin. Okay. If you're talking about vector between 2 other points in space, so let's say I'm talking about a point P at 3, negative 1, and also point Q at 1, 5. So 1 unit to the right, 1, 2, 3, 4, 5. 5 units upward. So this is the point Q. And if I want to draw a vector from P to Q like that, and if I want to write down what are the components for this vector PQ, we denote it something like this. So it points from P to Q. The tail is at P, and the head of the arrow is at Q. When we have something like that, we can get the components by looking at the coordinates of the head of the arrow and subtracting the coordinates from the tail of the arrow. So take the coordinates of Q, which is 1, 5, and subtract the coordinates of P. So we subtract 3 and subtract negative 1, which is the same thing as adding 1. And then we get vector negative 2, 6. So it goes 2 units to the left and 6 units upward. So that's exactly what we have pictured there. Okay, so in general, if you want to do this in 3-dimensional space, it's still the same idea. Look at the difference of the coordinates, but make sure to put the coordinates of the head of the arrow first, and then subtract the coordinates of the tail of the arrow. So that's the general way to compute something like that. Okay. When you have a vector, it's convenient to be able to compute the length or the magnitude of the vector. So you could use the distance formula, basically, to compute the length. We usually write it with the absolute value notation around a vector. I think the actual book uses this kind of parallel lines, but it gets cumbersome, so I just use the absolute value sign. So forgive me for not matching the book notation there, but I think the meaning is clear. So if I write absolute value of a vector, I mean find the length of the vector, and you use the Pythagorean theorem basically in 2D, and comes to something that looks like a Pythagorean theorem with just an extra component in 3D. And you might wonder, well, there's a pattern to this, right? If we're talking about one-dimensional vector, that's the same thing as square rooting a square of a number, because you make it positive. And you might imagine if there were such thing as 4-dimension space, and if you wanted to measure distance in this 4-dimensional space, maybe this is an appropriate formula. And it would be. Okay, so that's how we can compute vector of arbitrary many dimensions. It's harder to imagine, but the formula kind of expands in a well understood manner. And then just so I forgot to mention earlier. So there is such thing as a zero vector. So vector with nothing in any of the components. So the magnitude is 0, and the direction is kind of any direction. So if you go 0 units in any direction, you have the same zero vector. So in some sense, the information of the direction is kind of missing. But zero vector is something that's we're going to consider to be a vector anyway. Okay. So we have this new type of quantity called vectors, and I want to be able to do math with them. So I want to be able to do kind of arithmetic like with them, and we can work with them kind of like we do with algebra. So we want to be able to add vectors. So if we had two arrows, A and B, what's a reasonable way to make the definition of addition? So what we can do is we can take this, copy, okay, and we're also going to take vector B, and what we're going to do is we're going to kind of daisy chain them. So we're going to take one of the vectors and put the tail on the head of another vector, and then connect from the tail of the first vector to the head of the second vector. And we're going to call that thing A plus B. Okay. And you actually get the same vector if you do it the other way around as well. So if you can imagine vector B here. Oh, I didn't want to move them. I just wanted to copy them. Okay. And look at the vector A after B. Notice it makes like a parallelogram, and the diagonal across this parallelogram is going to be the addition of those two vectors. So it doesn't matter which way you add them. So A plus B is the same thing as B plus A. And the way to compute it component-wise is with the following formula that's kind of listed below. So you just look at the components of the two vectors and add those individually, separate. So it's component-wise addition. And this formula also makes it clear that it doesn't matter which way you add, right? So addition is commutative, and the same with vectors. Okay. We also want to be able to describe what it means to multiply a vector with a scalar. So if you had a vector A, and multiply it by a constant, like maybe like 2 or something, then we'll want to kind of stretch that vector, pointing the exact same direction, except kind of like stretch it by the factor constant c that's given there. If that constant is greater than 1, that means stretching. If it's kind of positive but less than 1, then it kind of shrinks it by the factor, like just like a regular multiplication with scalar. If we multiply by a negative number, we're going to consider it pointing in the opposite direction. So if we had vector a here, vector -1 times a, or just negative a, is going to be the same magnitude but pointing in the opposite direction. So I hope that makes sense. And if I'm multiplying by -2, it'll be stretched by a factor of 2, but the negative makes it flip the direction. The head and the tail of the arrow will flip. Okay. And this is really computed by component-wise multiplication, right? So each of the component is multiplied by the same scalar factor c, and exactly what the stretching and flipping will occur. Okay, so once we understand multiplication by scalar and how to add things, we could do subtraction of vectors as well, right? So what we could do is that if I want to subtract b from it, what we could do is we can kind of switch the direction it's pointing, but then now the negative becomes positive. So we're just going to add the difference, right? So A looks like this and B looks like that, or negative B looks like that. So this is going to be A minus B. Okay. So I hope that makes sense. And the way to compute it is pretty clear. So I'll leave that up to you, okay? Okay, so what I want you to do is kind of pause this video and do some arithmetic with these vectors. So I given you two 3-dimensional vectors A and B. I want you to compute the following 4 things. Okay. Well, let's work out the solutions. So 1, 2, -3 plus -2, -1, 5. If we add component-wise, 1 minus 2 is -1, 2 minus 1 is 1, and -3 plus 5 is 2. So that would be the sum of those 2 vectors. What we could do is we could just kind of compute the 2a. So that's like a vector, 1, 2, -3 multiplied by 2. So 2, 4, -6 minus -2, -1, 5, or maybe we could add 2, 1, -5, just kind of flip the sign on each of the components. And now I can just add the components together. Okay. Computing the magnitude, we could just do by Pythagorean's theorem. So that's 1 plus 4 plus 9. Square root of 14. That's not a nice number. And then we can compute the the magnitude of a minus b? Well, we could first compute a minus b. So let's see, a minus b, so 1 minus negative 2 is 3. 2 minus negative 1 is 3. And negative 3 minus 5 is negative 8. And then we're taking the magnitude of that afterwards. So 3 squared plus 3 squared plus negative 8 squared. So it's 18 plus 64, something like that. Okay. Let's see. Another common notation that we use is using the standard basis vector. So we use the vector version of the letter I for the vector of length 1 pointing in the positive x direction. So this is the vector 1, 0, 0. J is 0, 1, 0, and K is 0, 0, 1. So these are three different unit vectors. A unit vector is a vector that has length 1 pointing in the x, y, and z direction. And we could use this to kind of rewrite other types of vectors. So instead of writing negative 2 comma negative 1 comma 5, we could kind of rewrite that as negative 2 times the vector I, negative 1 times vector j, or when it's just negative, we could just say minus j, and 5 times k for the z component there. And sometimes I might write a vector this way. In fact, I kind of want you to get used to both types of notation, so I'm going to use them interchangeably. Okay. Another kind of useful type of computation is to sometimes we care about the direction, but we don't really care about the magnitude of a vector. So sometimes it's convenient to look at a vector and kind of, can I rescale it so the length is just 1? And we just keep the information about the direction. So we could do that by kind of rescaling it by the magnitude. So if I had a vector A, but want it to be length 1 instead, what we could do is we could first compute the length of that vector, which we actually already did, square root of 14. And if that's the length, so if we divide by that length, we can scale it down to length 1. So we could take the vector A and multiply by 1 over the magnitude to get 1 over root 14, 2 over root 14, and negative 3 over root 14. Okay. So this is type of manipulations that that will come in handy later on in the class. Okay, so this is where I want to stop the video. I'll see you later.